Okay, so welcome everybody. Today we are going to have Dr. Joyce McBeth talk to us about best practices of developing OER, and I'll just hand it over to her to get started.
Thanks, Isaac. So today I'm going to talk about a project that my colleague Jay Normand and I have been working on for the past few years for our Geology 201 labs in the Department of Geology at University of Regina. As a result of this project, we've got some best practices to recommend to other OER developers. And then also I want to touch on threshold concepts, which ties into the best practices, I promise. So I'm going to start sort of with that and then tell you more about our project and then tie it into the threshold concepts. So my co-authors on this, there's myself and Jane Normand, and then our student assistants, my graduate student, Caitlin Crawford, who's been the TA for the course for the past few years, and then some undergraduate students who assisted with the project as well. So I'm going to start off with an overview of threshold concepts, and this is at the very base level. I know there's probably people who watch this recording and have a much more nuanced understanding of threshold concepts, but I'm just going to introduce it at a very low level here and what they are and why we should care about them, especially when we're developing OER projects. And then I'll tell you more about our projects and where we've run into threshold concept roadblocks that we're working to address and how we're addressing them. Right, so let's start with what is a threshold concept. A threshold concept, and this is taken from Jan Mayer and Ray Land's book, Overcoming Barriers to Student Understanding Threshold Concepts and Troublesome Knowledge, which is an important publication in this area, and they've got other publications on this topic too. So a threshold concept can be considered as akin to a portal, opening up a new and previously inaccessible way of thinking about something. It represents a transformed way of understanding or interpreting or viewing something without which the learner cannot progress. So threshold concepts clearly are very important and are arguably at the root of what we're trying to achieve in higher education. We're trying to transform our students from just everyday people into specialists in our discipline. Here's another definition. This is they've actually Olanie, who is another practitioner in this area, and they're actually referencing Meyer and Land, but I thought this was a really useful regrouping of it, actually. So threshold concepts are transformative. I'll just paraphrase. Transformative, probably irreversible, integrative, sometimes bounded, and potentially troublesome. And what I want to highlight in this definition, we've already talked about transformative from Jan Meyer and Ray Land's definition, but the irreversible part, I think, is really crucial to highlight. Once you're over the hump, you can't go back. And another thing is sometimes it means we can't even identify it anymore. We may forget that we were ever on the other side. It becomes so intuitive to us. And so they can be, and that can be part of the troublesome part here. They're difficult to grasp initially. And then if your teacher is like, well, this is obvious, then it's even more challenging because it can create, some frustrating dynamics as instructors in our courses. So I wanted to give some examples of threshold concepts in the earth sciences, and I recognize our audience here. We've only got 2 earth scientists here, so you may not be past this threshold, and that's okay. But 2 of the really key ones are the principle of deep time, the principle of uniformitarianism. So this is the idea of geologic time spanning back the history of the Earth to 4.6 billion years ago. That's a really challenging concept for lay people to understand. And it depends on your upbringing and your education in your other times in your life. But that deep time concept is really critical for scientists. Uniformitarianism is a concept of gradual accumulation of geological, as geological processes happen, there's a gradual accumulation of change in Earth's on Earth's surface. And these two are intimately linked together. Another key threshold concept in earth science is 3D visualization. So as earth scientists, after we've completed our degrees, we are really adept at 3D visualization. This is something we totally take for granted. And I'll give you a really mundane example of this. So I was house hunting the other year. I'm still house hunting. And when you're house hunting, sometimes you see floor plans of houses. It is extremely easy for me to visualize what that floor plan would look like, to insert myself into that space and imagine what the whole place would look like. And I came to realize after discussing it with other people, this is not a ubiquitous skill. This is something we have training in as earth scientists that makes us really good at that, looking at a plan view, so a view from the top of something that's flat, and getting that 3D visual from that is something that we're really good at. And it's something we start training in our first year of our program, and we build on that throughout our program. But if we don't get that, we're really going to struggle. And it doesn't come easily to all people. It's harder for some people than others. This is actually quite a critical one relating to the lab. So that's why I'm highlighting it here. Another key threshold concept in earth science is rock and mineral ID processes, and this is also tied into the lab. So rock and mineral identification, basically, if you take a rock from the environment, a geoscientist should be able to use their eyeballs and other physical aspects, testing, perhaps like scratching the sample with different substrates, and looking at the grain size, things like that, about that rock, to understand where it came from, what processes have happened geologically to it. That's all integrated together. And this is quite a challenging process that is, it's not like a single threshold, it's a whole bunch of thresholds all pulled together. And it involves both like the kinesthetic part, the visual part, all of this coming together, and the concept of the processes. So it's really complex. And this is something we address in this course as well. Some examples, if all this geology stuff's like for you, I have some examples here that are more ubiquitous in science and in life in general. So the concepts of weight, mass, and gravity. People learn about this in their childhood and high school years. These three concepts, once you know them, it's impossible to like imagine a world where you didn't know what gravity is, right? It's just part of your everyday life, but it's so critical for so many ways in which we view the world. We need to understand how mass, weight, gravity work in order to interpret our surroundings and what's happening. Like, oh, that thing fell out of the tree. Oh, well, obviously it's because of gravity. We don't even have to think about it, right? It's just super intuitive. So but if you don't understand it, maybe you're a flat earther, right? Like it's a threshold concept that if you miss it, you're in trouble. So anyway, these are some examples of threshold concepts. Now, my pitch to you, why identify threshold concepts for our OER teaching projects? Well, because they're difficult for instructors to recognize, and because we often personally overcame these thresholds literally decades ago. We have done our undergraduate education a long time ago, and so it's hard to put ourselves in the bum on seat where our student is sitting and understand what they're going through right now, right? So once we've seen those threshold concepts and understand them, we can't unsee them. And we often forget that the threshold even exists. And so we may not even think to emphasize or break down certain concepts because we think they're so completely obvious to our students. And then we both integrate we have sort of an integrated frustration with our students because we're frustrated they're not getting it. They're frustrated because we're not explaining it very well. And we need to overcome this communication barrier, right? Threshold concepts can be very difficult for students to overcome. So that's very important in our OER teaching practices. We need to create resources that help our students to overcome those barriers and move forward. And that process can be uncomfortable and frustrating. Think about, when you've banged your head against a wall about some concept you're trying to learn and it's really hard. And, having someone say, well, it's super obvious and easy, that is like the worst thing you could say. And the frustration needs to be acknowledged that they're experiencing. And we need to acknowledge as instructors that our students go through these things and that part of our job is to help them overcome those thresholds. So I'd argue it's really critical for us to identify threshold concepts so we can do a better job at helping our students progress and get over those thresholds and make an OER teaching resource that's going to be useful more broadly for other people too. So we don't have a very big group of people today, so I'm not going to spend time on this unless you want to, but this is just a since it's called a workshop, so I wanted to have something that was a bit more interactive here. So something for people who are watching this to go away and think about, what are the topics that you find most frustrating to teach to students? Concepts that students are struggling with in your course, even though you consider that topic to be super duper easy. And it's sort of like puzzling to you. Why aren't they getting this? Why doesn't this make sense to them? You know, these like roadblocks that we encounter in our teaching, and everyone encounters these. And these are good questions to just kind of like have in the back of your head as you're teaching and think, okay, oh, this thing just happened. And just like, you know, interact with it kind of with curiosity, you know, like, why is this happening? And those are good examples where this is the kind of question that we ask of our teaching that can help to illuminate where these threshold concepts exist. And then if you have encountered that, and if you've taken steps to try and address it, what approaches have you happened upon that are actually effective for teaching these topics, or are your approaches not working, you know? And these are good things to talk about with other practitioners in our area. If this leaves your mind boggled, like where, you know, this is, I can't even think of examples of this, then here's some other ways I suggest to try and identify threshold concepts, and every discipline has them. So there's going to be threshold concepts in your work, undoubtedly. So if we look at exam results, there will sometimes be easy questions that our class is bombed on our exams. I had one on my exam the other day, and I realized it's not a them issue, it's a me issue, obviously. If they're all bombing on the question, there's either a threshold, or I haven't, you know, expressed myself very clearly with the question, or I haven't helped them navigate that question very effectively. So we had a conversation about it in my class, but another way to address it is through informal feedback. So what I've done with large classes to try and interrogate these issues is, if there's a question that I find I get weird stats on, say in a multiple choice question with one cohort, in the next cohort, I will specifically ask in a bonus question for informal feedback about that question. Why did you answer, for one point, why did you answer this question the way you did? And it's super informative, and sometimes helps to either identify a teaching issue where I'm introducing confusion, which happens, we're all human, or it can help us identify those threshold concepts. We can also ask them what the hardest question was in the exam, and you'll be surprised at how variable that answer will be. There will be students who found questions that you really didn't think were going to be hard, easy, and vice versa. So moving on to our specific project, and I'm going to give a couple of examples of threshold concepts we've run into and how we are attempting to address this issue. Not saying we're perfect, not saying we've got it all figured out, because they are by definition really challenging to address. So as an introduction, we were motivated to start this project, which is funded through the URegina OER projects fund. We were motivated to develop this project to provide resources for our students and ease the load on our lab instructors and TAs for this second year Earth Science class that we offer. We had resources for this class, but unfortunately they were lost when a previous instructor had moved on from the position. And so there was an opportunity here to generate a new resource that we could ensure was going to carry on for posterity. And then this is a secondary goal, like we're mostly motivated by practical reasons, but it is nice to be able to contribute to the larger pool of collaborative lab resources for earth science teaching globally. And already my colleagues at USask are interested in looking at what we've developed for our final project for this lab manual projects. There's one of the labs, or a set of labs, is relating to a final big project, and they're really curious to see more about that for their own development. So there's opportunities to iteratively work with other institutions and support one another in developing even better resources, right? The history of this project, it integrated we were taking this USask adaptation of a University of West Georgia manual that I had previously worked on. So I had done this particular project. We integrated that with existing URegina resources for this course. And we started this project in January 2021. So just to refresh your memory, at that point, we were still learning remotely. So for this first iteration of this course, our students were doing this entirely remotely, and we developed the project as we went. So each lab we would hustle, mostly Jane Normand would hustle to, and me too, a little bit, I'd help out as much as I could to develop each lab in advance of delivery. So it was definitely a big hustle the first semester, and then we iterated to improve it moving forward from there. I'm going to go through some more details about the project, but just a summary of those. I'll tell you a bit about our team structure, then our best practice recommendations overall, and some examples, and where we've run into threshold concept roadblocks and how we're addressing them. So our team leadership was myself and Jane Normand. And then we have Caitlin Crawford, our teaching assistant, who has, how many times is she? She's TA'd this course. She's on her 5th iteration now. So she's really experienced with the materials and this OER project. And so she gives us really critical feedback on how things are going and ideas for how to improve things. Then we hired a set of undergraduate student assistants. We had 2 senior undergraduates who did the bulk of the editing, alignment between Word documents that they were working on and the Pressbooks version for printing, which is, we're still putting finishing touches on that. And then we had a series of second-year undergraduates who worked as consultants on the project. So by that, I mean, they had taken the course, they were familiar with the material, they had used the lab manual, and they had strong opinions about it, and wanted to have some input into what we were doing moving forward. And so we asked them for their ideas about how to make it better. We got them to lay their eyes on the document and consider issues like accessibility. For example, one of the students is a international student, and so they could comment on wording that might be more confusing for international students and encourage us to sort of, keep it more easier to read, in some areas, and clarify things. So that was really helpful. One of the senior undergrads also had really great information on accessibility issues, so they also contributed to that as well. We communicated with our team via a Discord forum where they could post results and things and just communicate generally. Through Google Docs, we could distribute documents that way. It allowed us to see where they were at as things were going on. We had weekly, bi-weekly meetings over Zoom during the summer. Summers, we worked on this more intensely than during the semesters, just due to everyone's availability was better in the summers generally. So overall, this team approach worked fairly well. I would say one thing that definitely came up for us is that in particular the consultants group, but even the undergraduates, you have to have some flexibility with respect to employing student assistants for projects like this, because they have a lot of conflicting things in their life that can take them away from it, and they have to prioritize their schooling. Clearly needs to come first over any of this work, and we recognize that. They getting permanent jobs, and our 2 senior undergraduates both graduated while we were working on this project, and so we couldn't hold them back from getting permanent jobs in industry when they came up. Obviously, we wouldn't want to. And so you have to, well, you don't have to, but one of our take homes is it's really important to be prepared for that turnover in your group. We did get a little bit of pushback about having so many students working on this project. And I will say that the consultant level students, we paid everybody hourly. With consultants, it would be better to, like, if possible, to add up the hours and then just do a single payment at the end would be more efficient, because students' availability is so variable. If if it turns out they don't end up having a lot of availability, and that happened with at least one of the consultant students we were using, they ended up not really doing anything on the project at all, which was fine. We were paying hourly, but it's just it's better to do the hourly pay than employing someone full-time who might not end up working out. So that's a recommendation we have. Okay, so overall recommendations. My best practice lessons from, and I've integrated some lessons from the USask project as well into this list. So institutional support is transformative. Thank you, Isaac and company. This is really, really critical for moving these projects forward. If we didn't have this, it probably wouldn't be possible to make this an open resource. Like we would have probably done these labs anyway between Jane Normand and myself, but we would probably not have been able to take that next leap. So because it allows us to pay the students, and in the case of USask, we also employed a sessional instructor part-time to help with it. And it also helps, the other great thing about the institutional support is it helps us establish a timeline where we feel a bit of a whip crack. Not that it's held us back from extending that timeline. Thank you for the extensions, but it does help to have to plan in advance what your project's going to look like. Another best practice that's super important, and I've heard this in other OER project seminars before, so I won't dwell on this for too long, but it's really key to pick a good source starting point for your adaptation if you're not developing something from scratch. And most people take an earlier adaptation of something or a series of a number of adaptations and or a number of other projects and adapt them to make their project. So one key thing that we encountered in our projects, and I've been on a project where this was an issue and another where it wasn't, is tracking down images that are original and well referenced. If they're not, it's very time consuming to do it. And earth sciences, so in our discipline, there's a lot of images. Like every lecture I give has probably 50 images in it. And so this is not a trivial matter if you have not got well referenced, if you're not working from a well-referenced resource. I'm sure it's not as important in some other disciplines too, so that's fair, but for us, it's a really big deal. We found that developing the resource during the semester for immediate application, so we developed each lab and rolled it out during the semester. It was a trial by fire that semester, but it certainly was an efficient way to generate a first draft and get it out. Though we haven't published that on OER yet, but you can get something together really quickly. So in terms of assessing or encouraging people to take on these kinds of projects, something I guess for Isaac and company to think about is like if they can integrate it into a course that way, it does sort of pressure things, and it incorporates a lot of deadlines, right? Like you've got incremental deadlines throughout the semester that to keep your team on track. At that point in this project, we were not using the services of any undergraduate assistants. It was just the grad student and us. And actually, I think this was before we got our funding technically. So, but for people who are, planning a little further in advance than we were, that might be something to consider integrating into it. That'll move things forward more swiftly. I think it helped to have both lab and course instructors involved in the project. I haven't taught this course in a couple of years, unfortunately. I think if I was still teaching it, it probably would have helped us with moving it forward too, but because we always make some edits whenever it's offered again. But I've been obviously in touch with Jane Normand and Caitlin Crawford about progress and stuff. So anyway, this is, I think, a helpful thing for some projects. It's important, as I was saying, to incorporate flexibility into the student worker plans. So you're going to almost certainly have turnover in those student workers, especially if it takes more than 6 months to get the project done. Pay hourly. Don't even think about paying like a monthly wage. It's much safer to pay hourly because we have never had a student who is able to work full time. And that's fair. I'm not saying that to be derogatory towards the student. It's just realistic that they're going to have blocks of time rather than 40-hour weeks to work on these projects. This is a new addition from previous that I didn't have in previous versions of this talk when I've given it, but it's really important, we've discovered, to establish a plan for what computer applications and formats you're going to use for, especially when you're generating images. And we have a lot of images that we generated in ours. This needs to be established at the start, especially the formats. So to ensure that whatever your student workers are putting together, you can edit later. And this has been a bit of a challenge for us because we weren't as firm about it as we should have been. Like, one of our people was like, I'm going to use this thing. And I'm like, okay, as long as you can, export in an SVG file. And then they didn't. So, and then you got to try and chase it, right? So I would say it's best to start and require use of particular products or exports of certain files, and then tie that into regularly backing up all your work files from the students. And that we all struggle with this, but it's super critical for these projects. We had a situation where one of our students, for reasons outside of their control, lost access to the hard drive that they had been using to back up their materials on. Fortunately, we didn't lose much of their work, but we are learning from that experience that we should be using either a cloud resource for the backup and stuff, or we should meet with them every couple of weeks when they're working on the project to ensure that it's getting properly backed up. We used a diverse communication system for communicating with our student assistants, and that's worked pretty well. So we'll recommend that. Don't just rely solely on email. Super important, especially when you're working with student assistants who are near graduation, because very few of them use URegina's email system to begin with, and after graduation they're cut off, right? So it's really important to have alternate ways to contact them. We used a Discord forum for day-to-day, also Google Docs, Zoom meetings, and then Gmail address is their other contact info. And then my last practical best practice lesson is that after we're done, and you should ask the students how it's going. And I'm not talking about the student assistants, I'm talking about the students in the class. So it's really helpful to obtain constructive feedback from the students who are using the project or whatever resource you've developed, and use that feedback to help you iterate and improve the resource. And then also tying back into our threshold concepts to try and identify those areas where ultimately we need to do more development on the project. And obviously that might take us beyond, what the scope is of the present project. And that's fair. I'm not suggesting that they drag on forever, because I know that's a danger of these projects already that we struggle with, not just us, but lots of other people. So it's important to put that end mark on when the project is done, and then you can keep working for the second edition or whatever. But this constructive feedback is super important to help improve the resource over time. So this is just a quick slide with some recommended open source free tools for student workers to use. Inkscape, I really like this program. It's completely analogous to Adobe Illustrator or CorelDRAW. And as long as you save an SVG format, you can import that into these programs as well, and other scalar vector graphics programs. So it's really, really good. You can't work with photos in it. Like, you can drop a photo into it, but you can't edit the photo, or you shouldn't. It's not really a tool that's made for that. There are other tools for working with photos that one could recommend. And then it might seem obvious that MS Office would be the go-to for word processing, but students don't always have access to that software. And so, and there's other benefits to using software like Google Docs, for example, where we can, apps like Google Docs, where it's located in the cloud, so it's harder to lose the files. When we're working on, with all the projects I've worked on with Pressbooks, we've always had a backup Office copy or Google Doc that we're working from, so that we can make sure, for one thing, we're going to print it eventually. We'll have a print version of it, so we want to have a nice formatted copy, and Pressbooks isn't the greatest at formatting. And then also we have a backup that's like more physical, if you will, than the web version. So whatever programs they're using, just ensure that you can save to that preferred file type, whatever you have, that is flexible, like an SVG file for images that you can edit later, and you got to be firm about it, unlike us. So okay, so coming to threshold concepts for our Geology 201 course, I'm going to highlight 2, rock and mineral ID and our final project integration project. So let's start with rock and mineral ID labs. Here's a picture of a number of our students and TA Caitlin Crawford here working on their rock and mineral ID. I think they're actually working on this for the final project, but anyway, they have these kits that contain rock samples, and then they're looking at those and trying to identify them. And you can see they're all sort of lined up on this bench. They're interacting with one another a lot. You know, what do you think this is? And there's lots of teaching one another, which is a really important part. This is helpful for these labs, but it's also part of, in a more global sense, their training as geoscientists. Geoscience is a very teamwork driven discipline. And so they're developing those social skills, interactions, problem solving skills as a group, which is super important to their training. So it's a higher level goal, but it's also part of what they're doing here. So they practice their hands-on rock and mineral identification. There's 4 labs where they do that. The first 5 labs, aren't there? 5 labs. So there's the first 4, the first one is on mineral identification. Then they have 3 labs where they learn different kinds of rock types. And then the 5th lab, they are integrating that knowledge and identifying tricky, there's some kinds of rocks that look very similar to one another, but they're very different kinds of rocks. And so they're working on those false friends type rocks that look really similar but are totally different, and learning how to identify them and distinguish between them, which is quite tricky. So they're building their confidence through all these labs to that point where they can identify these challenging rocks. There's a logical process that students are trained to follow to do this. So for example, they would, if they had a rock, they would first ask, is it a sedimentary rock, an igneous rock, or a metamorphic rock? And they would look for key characteristics to try and distinguish between those 3 groups of rocks. The other thing that we're trying to develop here that is a bit more nebulous is their intuitive skills at rock and mineral identification. And I would put this combination of the logical process and the intuitive skills into a threshold concept here. Their intuitive skills still have a logical process to them. It's just much faster than going through a flowchart, and it's also more circular. They will, let's say, I mistakenly identified a rock as a metamorphic rock, and then as I'm looking at it, I discover a fossil in it. I would go, whoa, that's a sedimentary rock, not a metamorphic rock. And then I would go back and I would change where I was in my plan, but it's a much faster process, the intuitive skills, but it's very similar to the logical process. So it's an integration. And this is what we're aiming for. We want them to be able to speed through the logical process in a really intuitive way, and it's just second nature to them. And people who have a degree in geoscience are able to do this. It's a core skill, no matter what kind of geoscientist you are, and it's a major threshold concept. They will use these skills that they develop in these rock and mineral labs in at least, 6+ courses in the rest of their degree. So they're very critical skills that they're developing, critical and foundational, and also skills that they will apply as professional geoscientists after graduation. In almost every case, they will use it at least on a monthly basis. And so for some people, a lot more than that. So the resources that we've given to our students to do these rock and mineral labs, we have the samples and the kits. Here's another picture of a kit and some students working on their rock and mineral ID. We also have lab samples that are larger as well, that are easier to work with. We developed these kits during COVID because we needed to send them home with the students, and they're still useful. We also have our lab manual, and we've got images and diagrams. Here's an example here of various different rocks that are quite granular looking. So we're just comparing these different rock types and helping students to navigate distinguishing between them. We also have the TA and the lab instructor on hand to give them hands-on support and guide them through the process, and in a very as hands-off as they can be while being hands-on. So they kind of use a Socratic approach to teaching them the hands-on. So here's Caitlin working with this student. She's got, it's hard to make out here, but she's got a copy of the lab manual open on this student's phone, and she's pointing out some features of the rocks in the photo. And then of course, they're also working with one another. So that group work is a really helpful way for them to progress and work with one another to learn this kind of ID. We really noticed during COVID when we were, or I mean, COVID's still happening, but when we were working from home and they were learning from home, this inability to do the group work really hurt their progress. And it's terribly important as geoscientists for them to have those opportunities and to their learning in these labs. The last thing I have here is one of the diagrams from the lab manual. So this is an example of one of the flow charts that we put together. These are not uncommon. People have developed these before. We develop new ones for our classes just to match up with our sample sets and things. So you'd start by identifying key features and tests that you could run. So for example, does it react with hydrochloric acid? And then you drop a little bit of hydrochloric acid on there. If it does, then you go to the next chart. And so we can go through those charts. And then we have, oh gee, how many charts? 1, 2, 3, like 6 to 10 charts now, I think, for various types of identification in the course. So some of the challenges we ran into, well, the first challenge, of course, is just the ubiquitous challenge of integrating that logical process with the ultimately intuitive process. It just takes a lot of practice and experience with a variety of rocks. And one of our long-term issues is just everyone struggles with this in every geology department in the world. We have a limited number of samples our collection, and in the more samples they work with, the more practice they get and the better they get at doing it. So that there's not much we can do about that, but except to get more samples where we can, but we can work on these other tools. So we developed those flowcharts, and to try and help them simulate that intuitive process experience geology just used when they ID rocks. But the challenge with those flowcharts is, as I mentioned before, the process is not linear. There are gaps or spots where a practicing geoscientist who's working on the intuitive level would circle back in the flowchart, their virtual flowchart in their head, and change their path, and because the students haven't developed that intuitive side of it yet, that can introduce some confusion to them and frustration when they reach a dead end in the chart and they're like, oh, it doesn't match. What do I do now? Like they need to work on developing that circular move around skill, and they will, but it takes time and effort. And we would like to facilitate them making that leap more easily. And that's where the threshold concept challenge lies for us here. We also find that students could become overly dependent on the flowcharts, which could thwart our goal of having them integrate the intuitive ID process. And I don't mean like if they've memorized the flowchart, that's probably a good thing because it should move them closer to that intuitive ID process. The challenge is if they get locked up in it and too I guess stuck on it and go like, oh, I don't even know where to go because the flowchart said this, so we need them to have a flexibility integrated into how they're interpreting those flowcharts. So moving forward, we are making some revisions to the flowcharts to address some gaps. So the students had gotten stuck. They had the stuck issue, and we realized we'd left out one rock type in the chart. And this was a classic threshold concept moment. Well, we were like, well, it's obviously marble, but we were missing that one box, but we also struggled when finding that gap in the chart. It's like, well, okay, they missed, it was missing, so they missed it, and it's obvious to us, but we also want them to think about like what might be missing. So one thing we could do in future, and this is beyond the scope of the present project, so this would be next iteration of this lab manual when we'll ask for more money from the OER fund, but preparing an exercise or exercises where they can develop their own flowcharts or do sort of a fill in the blank kind of exercise. What's missing here to make them think about, where are the gaps here that need to be added in, and hopefully help them build those neurons or build the connections between the neurons in their own brains to develop their personal flowchart process in their head, the intuitive part. We'd also talked about developing some games to encourage students to practice their skills and make it fun. So testing each other, so gamification of this process, because of the flowcharts, it's a relatively easy thing to translate that to, say, like a card game or something where they have to, go, well, what, for example, like, okay, here's a rock, what, on a card, what feature or what test would you do to try and learn something else about this rock, So we can make up a little card game or something. That, again, would be a future direction that we'd like to develop for this course, but might make it a bit more fun and try and circumvent some of that frustration that can come up for students when they're dealing with these threshold concepts, because these are labs where students sometimes end up banging their head against the wall in frustration when they're struggling. Okay. So moving on to the final project, I wanted to highlight the issues we've run into with our final project. So this is a really innovative and awesome exercise. And this is one exercise that my USass colleagues are really interested in hearing more about, because at most institutions for this, the equivalent courses, you would do all these labs, but you would never integrate them together at the end. So this project that Jay Normand has developed over the years is a really effective way for students to integrate all the knowledge they've gained through this semester into a project that simulates a real world industry work experience. So they take the rock and mineral ID. I haven't talked about structural geology, but that's where we're looking at the different features geologically in the earth. So things like folds and faults within the earth. And they learn how to do mapping. To put that all together, they learn how to do cross sections where they get a slice through this and they can construct that just using the surface information. So it's a lot of practice in these other labs that they integrate together for this final project. And it's practical. So they'll use this experience in future courses, in at least 3 future courses in their programs, so the field schools, and in their structural geology course, at the very least, probably in other courses as well. They also develop a geological history of their study area after they've developed this geological map, which is, again, a fundamental skill that they'll use in many courses in the future. So this integration is really crucial. We have them present their data to the instructors, and then we give them feedback on, where the gaps are, where they could do more. And we try to, again, use a Socratic approach to help them see it for themselves. So there's a reflective aspect to this exercise. And then they actually integrate what they've learned from that into their final write-up for the project. So that's due after the presentation. So they have can learn as much as possible from it and further their learning. So here's an example of a cross section through this diagram here. So the cross section's going across this region here, I believe. No, actually, it's the one that goes from here to here. So it's going through this dike that's coming up here, and you can see the folds and things. And this is something a student has put together. So this is integrating their learning from the other labs. So it's pretty impressive, what they've put together. The resources for this project include the samples and kits for ID, again, that they used in the previous labs, and then they have additional samples for the map area. And then their earlier labs in the course, they can refer back to those. And then again, they have TA and lab instructor hands-on support, and they work in groups again. So once again, they're elevating their skills in teamwork, but they handed individual projects. And so we are avoiding the kind of stressful, like, oh, they did more work than me kind of thing. Like they are putting together individual projects. So it's teamwork in the best possible way for their learning and how we do it. So challenges we encountered with the project, students are often struggling with where to start with this. They struggle with putting their samples on the map and working out, so that in this diagram we see positions of different samples they have identified from their kits, and then they're working out what the geology is that is consistent with the sample positions on the map. It can be hard for them to figure out how to do that, even though we give a lab preamble that's very detailed. And we thought it was clear, right? Red flag, threshold concept, right? So after the first COVID working from home semester, so that semester in 2021, when we first brought out the manual, we asked, like, what can we do to make this better for you guys? And one of the students requested an exemplar to work from. And I thought, that would be good. And their insight too was that as a student with ADHD, it really helped them to see exemplars to process what was requested of them. And so we had one of our undergrad summer students put together a detailed series of exemplar maps. So this is the same map, and they're just going through different parts of the process in the map. And we've got, so it's examples of the map generation processes each step. We've got a cross section as well. I mean, I haven't shown it here, but it'll be similar to what's shown here that corresponds to this map. And then written explanations of the process at each step. Now, we haven't actually shared this part with the students yet, but last semester we shared these example maps with them. The results were not as we expected. We expected them to be like, oh, this is great. This makes it so much easier, and once again, we're struggling with our expectations of threshold concepts. They're still struggling. Red flag, we've got a threshold concept issue here, and that's okay. We're engaging with it and trying to move forward. So what our plan is moving forward for the final project, and these are things that will be in our final version of this OER project because it is quite critical for the first iteration. We're revising our exemplar a bit. Those written explanations of the process at each step, those will be in our final version, and the TA and Dr. Normand are using those this semester as well. So hopefully that will make a difference. This would be after this iteration of the lab manual, but potentially we could integrate, I was thinking, some interactive exercises maybe with the exemplar to guide the students in moving through each step to help them with that process. And then once again, though, because we've still got some mystery to why this exemplar isn't working as we'd hoped it would to help them get over the threshold, we need to check in with our students. Fundamentally, that's the most important process in this threshold concept overcoming plan is communication. So we need more informal feedback from them to help us identify where the learning gaps are here and to strategize about addressing them. And we're still working on that. So in summary, I've shared with you some best practice recommendations for OER projects more broadly. Consider the materials, or just very briefly, consider both the materials you're working with, so what you're adapting, if you're adapting a project or starting from zero, and also the practical aspects like your organization, your backups, your funding, things like that are all really important to consider in OER projects. I think usually when I've seen best practices talk, they mostly focus on the materials and sort of the way you roll it out in terms of the content, but these practical aspects, I hope that's useful to people to think about too. And then threshold concepts. It's really, I believe, really important to try and identify those to enhance the efficacy of your project overall. And keep in mind, it's an iterative process. We need to put boundaries and get things out, but if we can along the way try and elevate our treatment of these threshold concepts, will do a great service to our students and for students and other who are also exposed to these materials. So thank you very much to the AVP Academic and URegina OER Publishing Program, especially Isaac, for all your support. I want to thank my colleagues Carla and Michael at USask and UBCO for their work on the USask OER project and continued discussions about these things. They're really into this stuff. And then Heather Ross at USask for helping us with that OER project. the USask one, because they're so closely related to one another, and then our departments as well, and you for your time and attention. Thank you very much. And here's our contact information if anyone wants to get in touch with us. And if you have any questions, I'd be happy to address them, and so would Dr. Normand. No worries. Do you want to stop the recording, Isaac?